This is Radio TV Phono Nut, and first of all, wishing everyone a safe and happy Thanksgiving. And second of all, we have torn apart a little homebrew power supply. As you can see, this has a power transformer, a socket for a rectifier tube, probably a 5Y3, a toggle switch here to turn it on and off, and a terminal strip to provide our DC output voltage. So basically not a lot to this. And looking under the bottom, we see a filter choke and a couple of filter capacitors that look to comprise a pi-type filter network. As you can see, those filter capacitors are obviously bloated and shot, so they'll need to be replaced. But before we do any of that, we'll install a good power cord on this that isn't cracked, and check the condition of the power transformer. And then if that's good, then we can go with some new filter capacitors, stick a tube in it, and have us a little high voltage power supply for uses that we might need. I see a resistor here, and then another one on the outside. Those were likely installed as a bleeder resistor, so when you de-energize the power supply with no load on it, the charge off of the capacitors will bleed down, because let me tell you, a high voltage charge on these capacitors would get your attention in a rather unpleasant way. I know, I've been there before, and I'm sure anybody that's messed with this stuff for any length of time has also been there as well. Okay, we have the power cord replaced, and before we go any further, we'll energize the power transformer and make sure it's operating properly, as in we have the correct AC voltages being produced from the secondary winding. Okay, we're fully energized. We have our negative lead of the multimeter connected to chassis, which the center tap of the transformer connects to. Now, looking at one end of the high voltage winding, we have 357 volts. And going over here to the other end of the high voltage winding, we also have 358 volts. So that's good. And back to the other winding, if the meter probe will make contact, 358 volts, so that's good. Our high voltage winding is A-OK. Now let's check our filament winding. Okay, I've got 5.98 volts on the rectifier tube filament winding unloaded, so that's pretty good. And our other filament winding, which provides voltage to the other tubes that would be used on this power supply, that is right here on this terminal strip. So unloaded we have 7.3 volts. That's good. So that's right. Typically these types of power supplies, you'd use a 5Y3 rectifier, which uses a 5-volt filament, and that winding has been proven to be good. And then the rest of the tubes typically are 6.3 volt filaments, which that voltage is supplied here at the terminal strip. That voltage is there. And then we have our high voltage, roughly 700 volt center tap transformer, and that seems to be good. Now I'll check the continuity of the filter choke, which I'm sure it's good. And if it is, we'll go ahead and get rid of these two capacitors that we can just look at and tell that they're bad. And then we ought to fire this baby up and have a decent little general purpose 6.3 volt slash roughly 200 to 300 volt power supply for testing out radios or whatever. You know, it's not often that we need something like this, but there's been times when something like this would definitely come in handy. So let's get it working. Okay, the filter choke checks out. So I went ahead and snipped out started snipping out the filter capacitors, and accidentally cut the wrong thing. So we're going to have to replace this piece of wire here. And then I'll have to come up with a creative way to mount some newer capacitors in here. You know, the newer ones are a lot smaller than these older ones, so like I said, we'll have to come up with something creative to use to get those mounted. Okay, we have the new filter capacitors in place, and yes, I did J-hook them on to the original leads because I didn't want to upset how they had all these other leads soldered to various terminals. But I think we got it looking pretty neat looking. Okay, we need to find a rectifier tube and then we'll check this thing out, but first we'll test these. I think we know how they're going to test. They're probably dried out and wide open. Okay, electrolytic number 1. Yeah, it's extremely dry now. These types of capacitors go from being a dry electrolytic to an extremely dry electrolytic. Just out of curiosity, let's put some voltage on it and see if we detect any leakage. Yeah, at high voltage we have some leakage, so we basically have no I capacitance value and high leakage. So then of course the more voltage we place on it, the higher it leaks. So yeah, probably wouldn't have been that good of an idea to leave these in circuit and energize the power supply. Okay, electrolytic number 2, it's also ultra dry as well. Let's do the leakage test. So yeah, at high voltage, like what would normally be seen on these capacitors, that one is also very leaky. Okay, I borrowed a 5Y3 out of a radio, and at about 70 volts AC input to the power supply unloaded, we have about 271 volts DC here. So yeah, that's pretty stout. Now let's kill the power and see if it bleeds the capacitors down. It should, with those resistors in place. Yes, as you can see, it's bleeding it down. So those resistors are good for safety. Like I said, we wouldn't want to have a charge on these capacitors that would knock the crap out of you, and that's what would happen if there was no way to bleed down the charge on those capacitors. Alright, let's bring it up to 120 volts and see what we get. 443 volts, so we're pushing the working voltage limit of those capacitors. Would probably be better to use 500 volt capacitors here, but I don't have any of those, and under load this wouldn't be that high anyway. So there you go. I think we have this little power supply working just fine. Now, of course, I could replace this tube with a solid state plug-in rectifier, and I have one of those somewhere, but that really wouldn't be a good idea because the solid state rectifier is way more efficient than this tube is, and that would cause the B plus voltage to ramp up way higher than what those capacitors are rated for. And even under load, it would be way higher than what I would typically need for testing out a radio or whatever. So the only way we could go solid state here is to add another heat producing resistor to drop the excess voltage, and that's really defeating the purpose of a solid state rectifier. You might as well just keep the tube in there. And another reason I'd rather not go with solid state is because a tube rectifier is just a little bit more forgiving of a short circuit. In a solid state power supply, if something draws too much current, then you're probably going to pop your silicon diodes instantly. And a tube rectifier will withstand that a little bit better than a diode will, a solid state diode. And probably another thing I want to do to this, I'm not going to do it today because I don't have any right now, is I probably would want to add a fuse holder to this. And that way we could insert a fuse in the AC line, and that way if something shorts, it'll blow the fuse instead of burning up the power transformer. But being the careful person that I am, I think we can get by without a fuse for a little while anyway, because I try not to do stupid things like short out power supplies and that sort of thing. But no matter how careful one is, that sort of thing can happen. So at a later date, I probably will want to add a fuse to this. Okay, before we wind this up, I thought I'd draw out a schematic of our little power supply circuit for those of you who are already not familiar with such circuitry. And this is a textbook schematic of a vacuum tube based full wave rectifier circuit with pi-type filter network. So as I'm sure you know, most electronic equipment can't operate directly off of the 120 volt AC line. Number one, most of it needs DC voltage. And number two, most electronic equipment requires operating voltages that are either lower or higher, or in some cases they need both low and high voltages to operate. So that's why we need a power supply here. So we have our 120 volts coming in from the wall socket to energize the primary winding of the power transformer. And then on the secondary side of the transformer, in this particular case, we have three separate windings. We have a 700 volt center tapped high voltage winding, and then we have a 5 volt winding that supplies voltage to the rectifier tube filament, and then we have a 6.3 volt winding that supplies filament or heater voltage to the remaining tubes. So going back up to our 700 volt center tapped winding, our center tap connects to circuit ground, and if we were to measure across this winding from top to bottom, we would read about 700 volts. But if we measure from the top half of the winding to the center tap, we'll read about 350 volts, and the same goes if we measure from the bottom part of the winding to the center tap. So that provides our high AC voltage to the plates of the 5Y3 full wave rectifier tube, and then our 5 volts AC energizes the filament, which, by the way, this is known as a directly heated tube, which means the filament is also the cathode, which emits the electrons. Now, if this were an indirectly heated tube, we would have a separate cathode, and the only purpose for the filament or heater would be to heat the cathode to a degree that would cause electrons to be emitted. But in this case, the filament is the cathode, and that's just the way it is with these directly heated tubes. Alright, so we have our filament energized, and then also coming off of the filament, this is where our high DC voltage comes off. But we can't stop there, because if we stop there, we would have, in this case, since it's a full wave rectifier, we would have 120 hertz hum in the audio, and we can't have that. Now, if this was a half wave rectifier, such as a 35Z5 or 35W4, you would hear a 60 hertz hum in the audio. Now, when you encounter those problems, 99% of the time it's caused by dried out electrolytic filter capacitors. So what do we do to smooth out that ripple? Well, we have a filter network here, and in this case it consists of a 22 microfarad 450 volt capacitor, and then in the middle here we have a big filter choke, and then coming out we have another 22 microfarad 450 volt capacitor, which gives us nice ripple-free DC voltage here on the output that will supply the requirements of the piece of equipment that this is powering up and make everything happy. Now, this resistor on the output here, from the output to ground, That's our bleeder resistor, and its job is to bleed off the charge on these high voltage capacitors when the power is removed from the unit. If this resistor was not there, then these capacitors could hold a charge for quite some time, and that could provide a very nasty surprise if you touch those output terminals on the power supply. So in most cases, say you're working on an old radio, record player, TV, or whatever, there's not a bleeder resistor, and that's because the manufacturers of the equipment are counting on the circuitry itself to bleed off the capacitors whenever the unit is de-energized. However, if there's a malfunction in that circuitry that's not placing the proper load on the power supply, then these capacitors could still hold a nasty charge for a lengthy period of time. And when you go in there poking around to work on the set, then once again you could encounter a nasty surprise. And when you're talking about high voltage, high current power supplies, such as what's found in broadcast transmitters, that could take you out of this world ahead of schedule, so you want to be careful of that. Now, in the case of such thing as broadcast transmitters, they generally have bleeder resistors to bleed off the capacitors whenever the transmitter is de-energized. But they also include a device called commonly referred to as a Jesus stick, and the reason we call it that is because if you fail to use it, then you could be meeting Jesus before your time is supposed to be up. You may be asking yourself, why would they need a Jesus stick to discharge the capacitors if there's already a bleeder resistor in place? Well, because those bleeder resistors have been known to open up. So you just want to make doubly sure that those capacitors are discharged before you go playing around inside. And it doesn't matter if you're working on a broadcast transmitter or the power supply in a 5-tube radio. You just need to make sure of that. You don't want any nasty surprises there. And of course, with a little homemade power supply like this, you always want to use caution when operating it, because whenever it's energized, there's going to be a high voltage across those exposed terminals there, so you want to be careful of that. So that's about all I've got for the power supply. I'll give you an instance where a power supply like this might come in handy. You might remember a while back we had a Clinton Cathedral radio, or at least I think I made a video on it, where the power transformer was shorted, and that's when I pretty much tabled it, and it's been sitting in the closet for about the past 5 or 6 years, mainly because that set uses 2.5 volt tubes, and it's getting very hard to find suitable transformers with such a low filament voltage. They are available, but when you find them, they're usually costly, and I'm not going to spend a bunch of money on that radio. So probably what I'm going to end up doing is changing out the tubes to ones that use 6.3 volt heaters, and then we can use a more readily available transformer. But before we do all of that, it might be desirable for me to test the rest of the circuitry out in the radio before I go spending money on a new power transformer. But since this set uses 2.5 volt filament tubes, then of course we'll have to obtain a 2.5 volt filament transformer, which I think obtaining one of those will be easier than obtaining a standard transformer that would also have a high voltage winding on it. So we can use the 2.5 volt transformer for powering the tube heaters, and then we can connect this power supply to a variac, and then connect the output of the power supply to the radio itself once we disable the internal power supply, and then we can use the variac to adjust this power supply here to give us the desired B+ voltage, and that way I can troubleshoot the radio and get it playing again. And once I get the rest of the circuitry working, then I can go about ordering a proper transformer to put in there. So that's just one example of how a little power supply like this could come in handy. And now one other thing before I go, you might remember me talking about a gift that Shango 066 sent me several months ago, and I was going to do a two-part video on that item because we were having trouble with the YouTube, the video editor and the computer and YouTube and all that good stuff. Part of that footage was done with the old camera before it died, and I was going to make a video using that footage and then do another video using footage from the new camera. But since we have our video editing software temporarily straightened out, I think I'm just going to wait and do a full video on the whole thing, and it will be a fairly lengthy video, I feel sure. I'm making progress with it, but I've still got to order some parts to finish it up, which I will do as soon as possible, and then we will be able to put that together and do a video on that. I mean, I don't know exactly when I'll be finished with it, but we will get to it as soon as time and everything else permits. I mainly right now just wanted to do this quick little power supply video just to wish everybody a happy Thanksgiving and to do something quick and simple to put up so I could talk about where we are right now and everything. So with all of that said, I'll get off of here. I hope you got something out of all of this. I know it wasn't very involved, but at least it was something, and I do have a radio repair video that I put together, and I'll try to get that out this weekend maybe, and then hopefully the one after that will be the video on the item that Shango sent me, and I think you'll enjoy that one. Okay, enough for now. Happy Thanksgiving. Hope y'all got enough to eat, and more to come later.